I'm going to be talking to you about algorithms for robotic assembly planning with multiple agents. Some of the first research I did at Stanford was multi-agent automated racing. I developed a receding horizon controller based on game theoretic recursive reasoning that allowed these simulated agents to do these cool overtaking maneuvers. After that, I moved to the field of human driver behavior prediction and used some of the same game theoretic recursive reasoning concepts that I applied to that racing project and combined them with deep learning to develop advanced driver behavior prediction models. I also happen to have written an enormous survey paper about human driver behavior modeling and prediction. So from there, I moved to my current research, my thesis work, what has become my thesis work, which is on multi-agent automated manufacturing. So let me first motivate this with a few examples from history, both a little bit far back in history and a little bit more recent. So in World War II, in 1940, President Franklin Roosevelt announced to America, to the United States, that we needed to dramatically increase our air power in order to win this enormous war that was looming. And he challenged American aerospace companies and manufacturers to rise to the challenge. They did, and what this picture shows is the Ford Motor Company's Willow Run manufacturing plant, which was designed and built in less than 2.5 years by an enormous workforce of 42,000 plus people working around the clock in order to churn out the B-24 Liberator aircraft, which was a decisive factor in the Allied victory over the Axis powers in World War II. This factory pumped out about 9,000 of these airplanes, and at peak production, it manufactured, or one plane rolled off the line every hour. Of course, it wasn't at peak production all the time, but this particular feat of manufacturing had enormous consequences for the history of humankind. In more recent history, we are currently, hopefully, on the very tail end of the COVID-19 pandemic. In another feat of incredible manufacturing prowess, several American automakers and other companies teamed up to mass produce 80,000 respiratory ventilators, some of which are shown here, in order to address the shortages that might occur from the need for these respirators and these ventilators in so many hospitals around the country. So I share these two examples to make the point that manufacturing is important in human history. And these two examples are interesting because they also make the case for flexible manufacturing. In both cases, airplanes and ventilators, these products were outside the normal realm of what these manufacturers usually develop. In both cases, especially the case of the B-24, the Herculean efforts were required to retrofit existing facilities, design new tools, build this entire plant from the ground up in order to quickly get up and running. And so I asked the question, how great would it be to be able to perform these kind of feats without that dramatic Herculean upfront setup cost? Which leads me to the following segue. This is what you find in a modern factory, an assembly line. And it's great if you want to build a lot of one thing, for example, a car. But if you want to build something else, or more precisely, a lot of things, you need, excuse me, I'm going the wrong way, a flexible factory. And this kind of provides the vision that's been driving my PhD research for the last 2.5 years. So what is a flexible factory? It's a factory to which you can bring raw materials and instructions, and then out of the factory will come whatever the instructions tell it to build. If you want a different product, just put different materials and different instructions in, and out will pop different products. So as opposed to an assembly line model where the factory is designed to build one single product, a lot of a single product or a narrow range of products, a flexible factory should be able to build anything for which you can provide the materials and the instructions. So the question, of course, is what goes in here? How do you build a factory that can do these kinds of things? There's no single answer. There are surely a ton of factors that go into it. I'm going to speak about a few of them. But here is a little sneak peek into what I think one of these factories could look like. So what you're going to see here is a demo, a simulation of a team of mobile autonomous robots building a Star Wars X-Wing Lego set. So right now you're seeing where the different sub-assemblies are going to be built. Those were mapped out with those rectangular prisms there. And now the team of robots is moving through the factory. They're collecting objects from around at the periphery where the initial raw materials for the project are stored. And they're bringing the different materials, the building materials, to various staging locations throughout the factory, which are shown as these purple circles. After a robot or team of robots carries their cargo to a staging circle, it is unloaded and lifted into place onto the assembly. And as you see, the robots are avoiding collision with each other as they move through the factory. They're doing it quite quickly. You see, if you look closely, that these purple circles are changing in size at points. These circles represent the zones that are restricted to robot travel, except for robots that are allowed to enter them to deposit their cargo. So occasionally you see robots kind of dancing as they get stuck behind each other. Fortunately, they don't get stuck forever. And soon we'll see the completed assembly. I'll speed it up a little bit. This demo was such a long time in the making, so it makes me pretty happy to see it all coming together. So we're nearing the end now. Putting on the nose of the X-Wing, bringing together the wing assemblies. Hopefully the bandwidth is good enough that this video is coming across clearly to all of you. So here we are at the very end. The final assembly is complete, and these robots are ready to take it out the door. So, all done. So that's kind of my vision for what a flexible factory could look like, based on a team of mobile autonomous robots that work together to put together assemblies like this. Of course, it's not a complete picture. That would take a lot more than one PhD thesis, but it's a start, I think. So this brings me to an outline of the contributions of my PhD thesis. I would normally have put the Lego stuff at the end, but I felt that it would be helpful to discuss some of the challenging aspects of multi-agent manufacturing to put at the beginning. So first, we have a proof of concept Lego building system. The second major contribution is a discrete factory problem formulation that I proposed, and several methods for solving it, and some experimental results that show how those methods can scale. And then the final contribution of my thesis is the extension of this discrete factory problem formulation from contribution 2 to an online case where new manufacturing workloads are coming in the door of the factory on a regular basis. And now we need algorithms that can replan online to handle these new incoming workloads. And so I'll be speaking about each of these today. The Lego system, I'm going to give more of a high-level overview. For the other two, I'll dive a little bit deeper. So let's get started. How to build Lego sets with a team of multiple autonomous mobile robots. So we start with a project specification, which tells us what we're going to build. In this case, it could be a little tractor like this. The specification includes an assembly tree, which details how all the pieces fit together. And this assembly tree might be broken into sub-assemblies, and it might also be decomposed into building phases, which specify what order the different components of each assembly are allowed to be added to that assembly. So once we have our input, our project specification, we know that we're going to be moving things around the factory, and we need to figure out how the robots are going to transport them. This is what I call transport unit configuration. If we have big cargo, like the full assembly or sub-assemblies, or even some of the pieces, we need to figure out how to position robots around those assemblies in order to lift them and carry them and move them through the factory. So part of the Lego building system that I've developed, one of the first phases is the transport unit configuration phase, where each object that might need to be transported, that is assemblies and raw materials, we look at the 2D polygon that can fully inscribe that object, and then we consider where among the vertices of that polygon, those polygons, a team of robots can be arrayed to optimally carry the structure. So on a side note, when we're dealing with assemblies with arbitrarily complex non-convex geometry, we often need to simplify things so we have a more convenient geometry representation that we can use when we're doing collision avoidance, etc. So over approximating the assembly geometry with different simple shapes like spheres, cylinders, and prisms is an important component of this overall process that I'm describing here. So now that we've figured out how the robots can carry different payloads as teams, we need to figure out where we're going to build everything. As you saw in the X-Wing video demonstration, the different sub-assemblies and the final assembly are each built in different locations in the factory. So this is what I call construction zone planning. And the idea is that we want to find a layout that makes it particularly convenient to do the building processes. So right here, what you're seeing is what I call a construction zone plan or staging zone plan. Each red circle with a number in it corresponds to a specific assembly that's going to be built within that circle. The blue circles inside are bounding circles, which represent an over-approximation of the space occupied by the assembly as it's being built. And then the green circles represent deposit zones or drop-off locations for the different pieces of the assemblies, the components, to be deposited by robots or robot teams. And you might be wondering why some of these drop-off zones overlap. And that's because I've superimposed multiple different building phases within each staging location. But if we were to visualize just the plan for a single building phase, there would be no overlap between the green circles and these red staging circles. So we might also want a staging plan with a little more buffer room between the staging zones. But anyway, how do we construct this kind of plan? The answer is that we solve a sequence of nested radial layout optimization problems. So the idea is simple. If you have a central circle and you want to put some smaller circles around it, you want to arrange them around it in some configuration, and you may have, well, in our case, we do have preferred orientations for those smaller circles relative to the big one. This is a simple convex optimization problem to solve when we solve it in using the radial coordinates as our optimization decision variables. And so we solve a sequence of these nested problems to lay out the construction zone as seen here in an iterative fashion. So I want to show really quick another demo of another Lego set to kind of motivate why this approach is helpful. So here we see a triple nested, oh, sorry, this is going a bit too fast. Let me slow down. We have a triple nested assembly of Lego blocks, and you can see that the staging zones for the different sub-assemblies are arrayed again in this nested fashion. This is convenient because once a sub-assembly is built, it can be transported directly without needing to travel very far to the staging location of its parent assembly. And so this is a natural consequence of the way that we plan out the construction zone using the process I just described. So now we've planned out how robots will carry different objects, different payloads, whether they be raw materials or assemblies. And we've planned out the construction zones where the assemblies will be built. So now we need to actually figure out which robots will do which tasks. And so this is a complicated problem because we have robots need to work in teams. And additionally, the structure of the intertask precedence constraints can be very complex. And this is sort of described by what I'm showing here, which is a partial project schedule, which shows in order from left to right, kind of the precedence, the constraints on different tasks that can be executed by the robots. And so in order for a task to be executed, the task before it that has a line going to it from a task from the left side has to be done prior. And so this graphic is just meant to show that the process of assigning tasks and forming teams is quite complex. So once we've assigned robots to tasks and robot teams to tasks, we now need to actually execute the plan. And so we need, of course, for the robots not to collide with each other. And so to do this, we employ a multi-layer distributed velocity controller where each robot is running its own controller separately from the others. And the nominal controller is a clockwise, what I call a bug controller, or well, not just what I call, what is often called in the literature a bug controller. So here is a visualization of the same block we just saw, more robots in the scene, and the collision avoidance is turned off. So if you watch closely, you'll see that the robots, as they move along, they move around the purple circles that represent the staging areas. They always go around them in clockwise, in the clockwise direction if they're on a collision course on the way to their goal. Let me speed it up just a little bit. So again, you see robots colliding because I've turned off the collision avoidance for this part of the simulation. And each robot is running its own simple velocity planner that basically directs it towards its final goal. And if it encounters an obstacle, it'll go around in the clockwise direction. And that helps to reduce the risk of collision, even though it doesn't completely eliminate it. So after this layer, this nominal controller, we have a collision avoidance layer that basically, given the preferred velocities of all the agents, allows them to negotiate.
Sorry, just a quick question here.
Yes.
You kind of lost me here. So the clockwise bug controller, so there is still collision or there aren't collisions?
There are
I didn't get that.
Here. So basically the idea of the nominal controller is to give a planned velocity for each agent that will get it to its goal. And we've also imposed the restriction that robots need to go around in the clockwise direction so that there will be fewer collisions that are caused directly by the nominal controller. That said, there are still collisions that occur, as you can see. But I was just kind of trying to say that we've made a few design choices that hopefully reduce the amount of collisions that occur directly because of the nominal controller.
All right, yeah, thanks.
Yeah. But of course, there are still collisions that occur if we just run the nominal controller. So we have a collision, a negotiation layer essentially in level 3 that allows robots to negotiate in pairwise fashion what their velocity vectors can actually be in order to guarantee collision avoidance. Now, that's helpful, but it also isn't enough to prevent deadlock in the execution, where robots can get stuck trying to get past each other and can't move. And so to add another layer that sort of prevents this, although I can't prove that it does, it's just that empirically this has helped me to get these demos together that run all the way to completion, is the idea of dynamic artificial potential fields. So you may recall when seeing some of these demos, oops. Sorry, having a hard time. This might be the wrong one. Yes, so you see some robots in green. Those agents are active. That means they are involved with a build step that is active, meaning they can directly enter a staging circle to deposit their cargo or to pick up cargo. And so the idea of flagging an agent as active is part of the rationale for that is to show that some agents have higher priority than others. And you can see, for example, in this animation, that a bunch of robots are going to be crowding around the staging circle. And the higher priority, or the high priority agent, which is this one in green here, has to kind of force its way in. What you can't see in the simulation is that there's an artificial force field that is created around the agent that's trying to enter the circle with the green around it. And additionally, any agents that are close to this agent also exude a repulsive force field, virtual force field, that causes the agents around them to spread out and move away from each other. So basically, this has the effect, as a high priority agent is moving toward its goal location, of politely asking the other agents to move out of the way. And I found that this is very effective in reducing and in fact removing the gridlock that can occur if there's no extra part of this controller to encourage agents to get out of each other's way. So that wraps up my overview of the Lego system. Like I said, it's kind of at a high level. I just wanted to give a tour of that system, and also in describing the different challenges, kind of give a feel for how many different challenging aspects there are of this multi-agent manufacturing problem. There are plenty more challenging aspects that I didn't address. So now I'm going to move into a more simple formulation, but where we can address things like optimal planning more carefully. So we call this formulation precedence-constrained multi-agent task assignment and pathfinding. So the problem formulation is as follows. We have an environment, a discrete environment, that is, where each agent can only occupy each agent occupies a single grid location at each time step. We have robots in the environment, and we have objects. The objects need to be delivered to goals. This is only half the story, though, because these objects are part of a manufacturing project. So we deliver objects, 1, 2, and 3. And now that they've reached their goals, these objects can become inputs to manufacturing operations that take place at these darker gray squares, which are meant to represent, in a very abstract sense, manufacturing stations. For example, objects 1 and 2 are consumed by a manufacturing operation to create object 4. Object 3 is consumed by another operation to produce object 5. These objects are then available for pickup and can be delivered to their goals, at which point they become inputs to a new operation, which produces object 6, which can be delivered. And then the project is done. So so what we want to do is assign robots to tasks and then plan paths for them that avoid collision with each other and finish the project as quickly as possible. So that is the PCTAPF problem formulation. To map it out all on one page here, we have as input a project specification and an environment definition. The specification tells the precedence constraints between the delivery tasks and the start and goal locations for each object. And then the solution consists of an operating schedule, which basically details which robots are assigned to do which tasks and at what times they're expected to complete those tasks. And then the other half of a solution is the route plan, which is the actual trajectories that the robots follow through time to execute the operating schedule. So brief comparison to some problems that have been studied in the literature that are similar to our setting here. This slide, I won't go into detail on what each of these 6 other problems represents, but the point I'm trying to convey is that our formulation, PCTAPF, combines challenging aspects that are present in some of these problems, but in none of these problems are all of these aspects combined. And I'm showing here the characteristics of sequential task assignment, where robots might have to do multiple tasks in a row, collision avoidance, and cross-schedule dependencies between tasks, where different tasks are actually coupled together by different constraints. In our case, this arises because you can't pick up one object until it's been manufactured, which requires that 2 other objects or whatever be delivered in order for that operation to proceed. The same is true for our lifelong version of PCTAPF, which incorporates these aspects, and additionally, lifelong planning, online planning. So just another quick aside, I like to look at the task structure of these different problems. Each of these graphics, you can tell, just move in a straight line across, and that's meant to show that the tasks that can be assigned to robots are all independent from each other. In our formulation, on the other hand, the different robot tasks have these intertask constraints like I just described. So back to the PCT-APF formulation. How do we solve one of these problems? How do we solve it optimally? One way we can do it is to formulate it as a dynamic network flow problem. Oops, that's not supposed to play. I should be using my keyboard and not my mouse. Okay. So let's consider this very simple environment. It's a one-dimensional environment that's only one grid cell wide and then six long. There are two objects to be delivered, objects 1 and 2. Object 1 has to be delivered first. And so that a solution looks like this. I'll play it again. Robot 1 collects object 1, and then robot 2 can take object 2 to its goal. Great. So in order to formulate PCT-APF as an integer flow problem, and you'll see in a moment why I've chosen to do this with a one-dimensional environment, we first take the environment graph and we extend it through time, where each vertex shown here in this time-extended environment graph corresponds to an environment vertex at a particular time step. And now our task becomes to find flows that move through this graph from the starting locations to the goal location. So we have different kinds of flows. One is a robot flow, which robot flows are shown in blue. Object flows are shown in orange. And so it might not be immediately clear how finding these flows corresponds to solving a PCT-APF problem. But if you look at this video again, you'll see that essentially what this flow represents the solution through time to a PCT-APF problem. So there are a few constraints that have to be, well, first of all, let me clarify that a flow in this case is a value assigned to each edge in this time extended environment graph. And so if you see the color along an edge, that means the flow value on that edge is 1 for that particular kind of flow, otherwise it's 0. So there are a few constraints on the flow, on the different flows in this problem. They can be encoded in this hideous mixed integer program here that I'm going to spare you the details, but I'm just showing you so you believe me that it actually is a real thing. So back to here, this little graphic, some of the constraints include flows have to start at the start locations for the robots and the objects. For the objects, flows have to terminate at the goal locations for each object. And an object can't go to another object's goal, it has to go to its own goal. For an object to move, it has to be on the back of a robot, which is why here, when you see the object moving along these non-horizontal edges, it has to be paired with a robot flow. Also, we have our precedence constraints. So we have that this object flow here may not leave its starting location until the object flow associated with object 1 has arrived at its goal location. And so there are some other constraints that are kind of the nitty-gritty details of getting a flow, correctly formulating an integer flow problem. For example, they have to be connected, so you can't just have random flow values because that wouldn't really be a flow anymore. It'd just be a bunch of disconnected values. So point is, you can solve PCT-APF optimally as an integer flow problem. This is nice because you just formulate the problem and then you pass it to a black box, an off-the-shelf solver, and it solves it for you. So fortunately for me, this is only kind of a good idea. Otherwise, I wouldn't have much of a thesis to defend. So look at this very simple solution. 2 objects, 2 robots. It takes 22 seconds for a state-of-the-art commercial solver to solve this problem represented as a flow problem. If that doesn't sound too bad to you, trust me, that's pretty slow. Here's another problem. 4 robots and 2 objects takes 85 seconds for the commercial solver to solve. And then this problem, two objects and 2 robots, takes 321 seconds to solve, and the flow solver actually doesn't solve it. What I just showed was a solution computed by another solver, which I'm about to introduce to you. So the point of this page is, yes, we can formulate PCTF APF as a dynamic network flow problem and solve it with a brute force method. But this is not the solver we're looking for because it's really slow and doesn't scale at all. So now let me introduce to you a hierarchical PCT APF solver, which I developed with collaborators in the group that Mac talked about. This was kind of the kickoff algorithm for my thesis. So it's got a lot of moving parts. I am going to focus on level 1 and level 4, but let me first describe to you at a high level how the algorithm works. So the algorithm decouples task assignment and route planning. So we start at level 1, and level 1 says, okay, I have a PCT APF problem. I'm going to assume for a moment that we don't have to worry about robots colliding with each other. And under that assumption, I'm going to assign robots to tasks in such a way that I think they can complete the project as quickly as possible. And then level 1 says to level 2, hey, level 2, I have just assigned robots to these tasks. Can you now take care of planning the route plan for me? Make sure that no robots collide, and make sure that you go as fast as you can, or rather that you return a route plan that finishes the project as quickly as possible. Level 2 says, sure thing, let me talk to levels 3 and 4, and we'll take care of that. After some discussion, level 2 comes back and says, okay, level 1, we have this route plan. What do you think? Level 1 says, okay, this is good, but I thought you would have been able to do a little bit faster. Looks like you had to delay the project a little bit in order to avoid having robots bump into each other. That's okay, I forgive you, but let's try again. I'm going to try a different assignment of robots to tasks. In fact, the next best assignment that I can think of, and see what you can do with that. Same thing happens. Level 2 comes back to level 1 and says, okay, what do you think? Level 1 says, oops, forgot how many times I had done that little animation. Level 1 says, that's great. I've been keeping track of the best route plan you've given me so far. And the next assignment that I was going to try couldn't possibly be completed quicker than the best route plan you've given me so far. So we're going to go with that. We've got an optimal solution. Awesome. So that's how the algorithm works at a high level. Now I'm going to describe to you how we formulate the task assignment problem that is solved in level 1. So this is called an assignment matrix. It has one row for each robot and one column for each object. If we put a 1 in row 2, column 4, this means we are assigning robot 2 to do task 4, deliver object 4. What if we put a 1 here as well? We're saying robot 2 needs to do tasks 3 and 4. This is perfectly fine. We have more tasks than robots, so at least one robot is going to have to do more than one task. The trouble here, though, is that this way of representing the assignment of robots to tasks doesn't tell us which order a robot should do the tasks in. So we need something more. And the way we do that is by adding 6 rows to our assignment matrix. And I call these dummy robot rows. The idea is that we pretend that each robot, after it delivers an object, will disappear at that location where it delivers an object. In its place will appear a new robot, which we'll call a dummy robot. And the dummy robot's number is the number of the object that was delivered by the robot that just disappeared at that location. So if we put a 1 here, we're assigning dummy robot 3 to task 4. We are saying, in effect, whichever robot just delivered object 3 is now going to be assigned to deliver object 4. So if we put a 1 here, we're assigning robot 2 to task 3, and then dummy robot 3 to task 4, meaning robot 2 first does task 3 and then task 4. So now we have converted our time-extended assignment problem into a one-off assignment problem by making by using this simplification or this transformation where we assume robots disappear and new robots appear. Okay, so what if we put a 1 here? We're assigning dummy robot 2 to task 2. That means whichever robot just completed task 2, next you're supposed to complete task 2. Now that's a very silly thing to ask any robot to do. So we want to prevent that from being, that kind of assignment from being made in our assignment matrix. Same thing for all the assignments on the diagonal. No use wasting time here. So what if we put a 1 here? We're assigning the robot that just delivered object 4 to deliver object 2 next. That seems pretty harmless, but if we look at our project specification, we recognize a problem. If we say that the robot that just delivered object 4 should now deliver object 2, we are then asking that robot to go back in time, which is an even worse thing to ask of any robot to do. So we want to save our poor robots from this kind of grief as well. So that is excluded from the list of legal assignments. Same thing goes for any task that is a predecessor of the task associated with the dummy robot. So we exclude all of these entries from our assignment matrix. So great, now we have constraints on where we can put 1s in our assignment matrix. By the way, I neglected to mention this earlier. To complete the assignment matrix, we need a 1 in each column. And we can only have a 1 in each row as well. So once we have a 1 in each column, we are done. And we have to make sure that there's no more than one single 1 in each column. All right. So now we need to, of course, we want the very best assignment, which means we need to keep track of how long it will take the robots to do a particular assignment. This vector here, a vector of zeros, represents the initial time of these 3 robots. We assume that they become available at time 0. And this vector down here is the initial time of these objects. We assume that the 3 initial objects become available at time 0 as well. For the other 3, that depends on when they are manufactured, which depends in turn on when their predecessor objects are delivered, which depends in turn on which robots are doing the delivering, and also depends on what those robots might have done beforehand. So these next 6 entries of this vector, of course, correspond to the initial times at which to the times at which these dummy robots appear, which again, in the same way as I just described in that very circular way, depends on what those robots did before and how long it took other robots to do their tasks that were predecessors, etc. Then finally down here, this vector represents the time at which each object is actually delivered and the task is complete. In order to determine what the lower bounds on these different times can be, the ones that are not already written in as zeros, we need to reason about how long it'll take a given robot to move through the environment from a start location to a goal location. And the distances through this environment, assuming no collision between robots, allow us to put a lower bound on how quickly an assignment can be completed. Okay, and we care, of course, about this very last square, which corresponds to the delivery time of the final task, task 6, because when that's done, the project's done, and that's what we care about, finishing the project as quickly as possible. So this whole assignment problem that I've just described can be encoded as a mixed integer linear program. These constraints define the assignment matrix and specify only 1 1 per column, or exactly 1 non-zero entry per column and only 1 non-zero entry per row. These constraints are the red X's that I just showed, or some of them, that is, that basically make all assignments illegal if they require a robot to go back in time. These constraints define the initial times of the robots and dummy robots. These are the constraints that make sure that no task can begin until its predecessors have been completed. And then these constraints define the make span and the delivery times of the robots. So we can solve this problem, and we have an optimistic task assignment, which optimally solves this task assignment subproblem if we assume that robots can't collide. So I've just described what happens in level 1 as part of the task assignment that's passed down to the route planner. Now I'm going to jump down to the final level of the route planner to describe what I think is kind of the secret sauce, the secret element of our route planner that makes it so efficient at avoiding collisions. So to do that, I am just realizing that I forgot to load this. How absurd. Everything put together just right except this. So while I do that, actually, I don't think that. Okay. So level 4, what I'm about to tell you about, receives a request from the level above it in our route planner that says, hey, I need you to plan a path for a robot from its start location to its goal location. This is how much time I'd like it to take, because if it takes any longer, the whole project will be delayed. Now that amount of time that's allotted might be more than enough to compute the plan, but that can vary from task to task. So now I'm going to show you a demo of how this part of the route planner works. So let me open this up for you. Don't peek because I have to reset this. Pretend you're not seeing any of this. Okay, we're good to go. Actually, now we're good to go. Okay, so we have 3 robots here, and they're each trying to get to one of these green spheres. And you'll see which ones they're going for as I play this animation. So you may have noticed, if you're watching closely, that we had 2 collisions. So I'm going to plot the trajectories of the robots in 3D so you can see where they collided in time. So time is now our 3rd dimension here. And you see that this robot with the zigzag path collided with both of the robots that are taking straight paths. So we're going to assume right now that we're trying to plan a path for the zigzag robot, and that the paths for the other robots have already been planned. So ideally, we'd like to plan a path that doesn't collide with these 2 other paths. And so that's the responsibility now of this A* SC level of our route planner. So let me animate for you the search process if we plan the path with the regular A* path planning problem. So here you can see that proceeding here. A* expands a search tree of states, and it in best first order, and states are scored according to how far they are from the goal plus how far they are from the start state. So here we see this is the path that was returned by A*. It's exactly what we just saw. And the reason we have 2 collisions here is because A* is completely ignorant that there are 2 paths already planned for other robots, and we should be trying to avoid collision with them. One simple way to augment A* is to add a tie-breaking function to the cost function so that it breaks ties for search states in favor of those that don't have collisions. So we watch again, same algorithm, but now with a tie-breaking cost function added to it. You'll see that when the search tree encounters a collision, it will try to find an alternate path if that's possible, to find an alternate path that doesn't have a collision, but still reaches the goal in minimum time. So you'll see now at the end of this search that we recover a different path, which is a little bit better because it only has 1 collision rather than 2 collisions like the first one. So here our tie-breaking collision cost function has come in handy, but we still have a collision. Now remember what I said at the beginning, that we only care about how long it takes the whole project to run to completion. And it happens often that one robot or several robots have wiggle room in their individual schedules, meaning those robots can afford to wait to be delayed 1 or 2 time steps before reaching their goal, and that will not hinder the overall project, that will not delay the overall project. So I'm going to show you now our version of A*, which has not only the collision tie-breaking function, but also allows the algorithm to use up slack in its schedule, meaning to use up that wiggle time if necessary to avoid collisions. So here's an animation of that. So similar search procedure as before, we encounter a collision, and now you see the algorithm is trying out states that allow for a delay. And you'll see this clearly when the path is reconstructed. So there's the reconstructed path, and you can see there are no collisions with the other paths. If I play the animation of the robots actually moving along these paths, we have this happy result where we don't have any robots running into each other. Very exciting. So now I just want to take a step back and show you why it is that our variant of the algorithm is effective at planning in these kind of scenarios where there is room to be delayed, where you still want to find the shortest path if possible, but you have room to be delayed. So right here, I'm going to animate the set of all paths that reach the goal in minimum time from the start. So this is all the possible paths this robot could take to reach the goal in minimum time. Now I'm going to animate a different set of paths, which is the set of all paths that the robot can take to the goal that reach the goal in minimum time or only have one time step of delay. And you can see that is a larger set of paths that can be returned by the algorithm. And that's what allows us to, and because the algorithm can search this larger set of paths on demand when it needs to, it can avoid collision more effectively. If we were to allow 2 time steps of delay, the optimal reachable set grows even larger. And so the reason our algorithm is so effective at avoiding collisions, this low-level path planner is because it will search through the full space of plans that do not delay, that do not run out of slack, that is, that don't cause more than the delay that's allowed, and that don't cause collisions. And it will search over this, it will search through this, this set in such a way that it doesn't waste time searching outside of the shortest path unless that's necessary to avoid collisions. So just really quick, that all of that behavior is encoded quite simply in this 5-level tie-breaking cost function. The first 2 layers, or the first cost, is what allows the robot to use up that wiggle room, that slack. The second breaks ties in favors of paths that don't have conflicts. And the last 3 favor states that are closer to the goal. So now I just described the highest and lowest levels of our algorithm. I've got more information on the algorithm in the appendix if anybody cares to ask questions after, but for the sake of time, we're going to move forward. But hopefully that came across clear that this route planner, this path planner, does some pretty cool stuff. So let's look at some results from our algorithm. Here in the upper left, we see a plot of solver runtime for various classes of PCT-APF problems. I'd like to draw your attention to this right here. This represents problems, 16 of them, that have 40 robots and 60 tasks. And the solver solves these problems all in about 2 or 3 seconds. Whole problem done. So that's pretty good compared to the flow solver, which I described earlier, which takes sometimes 321 seconds on a problem with 2 robots and 2 tasks and doesn't actually solve it at all. So now you may also be wondering, okay, there are also some problems clearly that this solver struggles with as well. That's true. These problems are specifically those with a high number of tasks compared to a low number of robots. And as you can see here, for all the tasks with all the problems with 10 robots and 60 tasks, the algorithm times out 100 seconds and can't solve them. And mathematically, these problems resemble more and more a traveling salesman problem as that ratio of tasks to robots increases. So it's not surprising at all that the algorithm struggles here. But it is, of course, worth noting that for cases like this, we would do well to employ suboptimal approaches that have better runtime guarantees. Over here on the right, I just want to point out, these are the results for the route planner. For any of these problems, once we have an assignment of tasks, the route planner can solve the route planning subproblem in well under a second, even for the largest problems. I think that's pretty exciting. And it's clear from this plot on the left that the struggling, our solver struggles, it's the assignment portion of the solver that struggles in the top level, not the route planning levels. So now, here's just a quick video of a very large problem that our solver can solve in 52 seconds. It has 70 robots and 200 tasks. I think that's pretty cool that it can scale so well compared to, and by the way, this is an optimal solution. That's the fastest that it can be done. I think it's pretty cool that it can scale so much better than the flow version, than the flow solver, excuse me, that we described previously. So that wraps up the discussion of PCT-APF, the discrete factory problem, except that we are now going to talk about a lifelong extension of PCT-APF, where we have tasks or new workloads that arrive over time. So let's say the robots are all busy working on this project, and then a new project request arrives as they're in the middle of what they've been doing. What should they do? Now another one arrives, and they need to now balance work on all these projects at once. So here's a little video of what that looks like. So this is very similar to the problem we just described. In fact, it is the problem we just described, with the exception that we have new workloads arriving over time. But now we have this interesting scenario where we don't just want an optimal solution. We want to make sure that the solver, whatever solver is doing the replanning when a new workload arrives, can finish quickly enough that we're not wasting time replanning when the robots could be getting to work. So I'm going to talk to you about a family of solvers that I've developed to address this problem. Make sure I don't run over my microphone here. So there are two main replanning paradigms that I'm going to discuss. We call these reassign free robots and merge and balance in the bottom. The idea is, if we're looking at this video that I just showed you, at any moment in time, many robots already have tasks assigned to them, and they're working on those tasks. When a new workload arrives, the question arises, should we cancel some of the tasks that have already been assigned to robots, or should we just add new tasks on top of them? It's a very challenging question, and there's not necessarily a right answer. It depends on how quickly new tasks are coming in, what the environment looks like, how many robots there are, etc. But there are two sort of main paradigms. One is we do reassign, or we do cancel tasks and reassign them. The other one is we only reassign free robots to new tasks. That is, robots that are done with their previous tasks. So here I'm showing an animation of the environment on the right with the existing workload. And on the left, in each column, these represent the robot itineraries, the sequence of tasks assigned to any given robot. And as we step forward in time and receive a new workload, on the left is the paradigm where we do not reassign, we do not cancel previous tasks. We just add new tasks on top of them. On the right, we have a solution where we are allowed to cancel tasks, and then we can move those tasks around and add new tasks on top. And you can see over time steps that these itineraries assigned to these robots look different in these two paradigms. And again, on the left, we have the case where we never cancel tasks, we just add tasks on top. On the right, we are allowed to cancel tasks and then shuffle them around and add new ones. So let's compare these two approaches.
Sorry, just a quick question.
Yes.
In your previous slide, what's the color scheme for the dots?
The color scheme, sorry, if you look over here at the workloads that are arriving, each workload has its own, is color-coded.
Right, okay, yeah.
So that's the color scheme for the dots. It's really hard to track visually, but if you stare at it for a really long time, then you could make some sense of it. So, so let's compare these two approaches. On the left, we are allowed to cancel tasks. On the right, we are not allowed to cancel tasks. So you see the projects look like they're arriving at slightly different times. That's not actually the case. What's happening is that the solver on the left is letting the project through more quickly. It's jumping to its new plan more quickly. So it's clear from this alone that the robots are making more progress on the left side than on the right in this particular case. That doesn't necessarily mean that the approach where we're allowed to cancel tasks and then reassign them is always better, but in this case, it outperforms the approach where we only reassign free robots. So let me show you just some brief results. So again, merge and balance in blue is the approach where we are allowed to cancel tasks and then reassign them. Reassigned free robots is where we don't cancel tasks, we just assign new tasks to the robots that are free. So I've plotted some results for these solvers and 2 other solvers that I haven't described here. As you can see, in general, the merge and balance solver does better. And these results, let me describe what we're actually looking at. We're looking at the make span of each project request that arrives in the factory, each new workload, how long it takes to complete that workload from when it arrives, that is, versus, so that's on the y-axis. And then on the horizontal axis for each of these plots is time. So the time at which each new workload arrives. And over here on the top left, we're looking at a plot where lots of big projects are arriving quickly. And so the factory tends to fall behind slowly. But we see that the merge and balance approach, which is allowed to cancel tasks, falls behind more slowly than the reassign free robots tasks, which does not cancel tasks. And this holds generally true for the problems that are shown here, except for here on the far right, there's no, or the lower right, there's no appreciable difference. This corresponds to a case where the projects are arriving not very quickly in the factory over time, and they're not very big either.